This is the first slide. This shows, this is the title of our subject, antennas and wave propagation. And coming to the history, antennas were built in 1888 by the German scientist named Hedge. So coming to the introduction, it is about the antenna definition. That is, antenna is nothing but a conductor which converts electrical signal into electromagnetic signal or vice versa. And similarly, the antennas are of two types by the functionality. The transmitting antennas and receiving antennas. Transmitting antenna is the antenna which will radiate the electromagnetic radiation, and receiving antenna is the antenna which collects the electromagnetic radiation and will generate the signal at its terminals. Transmitting antenna is generally connected to the transmitter, and receiving antenna is generally connected to the receiver. Basic structure of the antenna. So already seen that the antenna is nothing but a conductor. It is capable of radiating and receiving the electromagnetic waves. Generally, we are applying some excitation to the antenna. By applying the excitation, it will be able to radiate or receive the signals. And here there is one a theorem called reciprocity theorem, which states that the characteristics of a particular antenna are same when it is acting as a transmitting antenna, and similarly when it is acting as receiving antenna. Sometimes antennas may also will contain reflective surfaces along with the antennas in order to increase the directivity. Antennas can be designed to transmit the radio waves in all directions equally. The type of antennas are called omnidirectional antennas. Why antennas are generally needed? So generally the need of antenna will be arising when two persons wanted to communicate between each other when there is no wire communication. That means these antennas are generally needed when there is wireless communication. So these radio waves are electromagnetic waves which carry the signals through the air at the speed of light. That means radio waves are having the speed as equal to the light velocity. The radio waves are also used directly for measurements in technologies including radar, GPS, and radio astronomy. And generally, we observe the antennas in the laptops also. Those are hidden in the laptops. Those are also generally seen in our AM radios also. Generally, the people are using AM radios in the olden days. In that radio, inside the radio, so there is antenna inside the radio. There we see. Where used? Antennas are used in systems such as radio and television broadcasting, point-to-point radio communication, and wireless LAN, radar, and space exploration. Antennas are mostly used in air or outer space. And in underwater communication also these antennas are generally used. And the next one is radiation mechanism. Here in this, if you see in this picture, at one end we are applying a generator. We are connecting a generator. On the other end, the radio waves are being generated. In this way, uh, we are applying energy at the input. At the output, we are getting the electromagnetic radiation. A part of the energy is escaping from this antenna. So that energy is called radiated energy. So if we take two wires, what happens is that the top wire is acting as a radiator and bottom wire is also acting as radiator. Here the uh, here if you see, radiation of the top wire will be cancelling the radiation of the bottom wire in some way. That is generally happening. So in order to increase the amount of radiation, we have to we have to uh, enlarge the output end. So by enlarging the output end, that means the other end, as shown in the above figure, automatically we can increase the radiation so that the top wire radiation is not completely cancelled by the bottom wire radiation. So in this way, we can increase the radiation efficiency further by enlarging the output end like this. Types of antennas, omnidirectional antennas and directional antennas. So omnidirectional antennas are nothing but these antennas will radiate equally in the horizontal plane. These are equally radiating in horizontal plane, and they will provide unequal radiation in its perpendicular plane. That means in the vertical plane. That means in one plane only they provide equal radiation. In the perpendicular plane, it is not able to radiate equally. And directional antennas. So these antennas are generally intended to uh, preferentially radiate or receive in a particular direction or directional pattern. That means these antennas will provide more radiation in a particular direction. So that is about the directional antennas. Resonant antennas. So according to the length of the transmission lines, so these resonant antennas can be divided. These are categorized into two types: resonant and non-resonant. And the resonant antenna is nothing but an antenna where its length is equal to exactly equal to the multiples of half wavelength. So, and in the non-resonant antenna, the length of the antenna is not exact multiples of half wavelength. Radiation pattern. If you see for an antenna, radiation pattern is nothing but a three-dimensional graph of the radiated power by the antenna as a function of the space coordinates. If you see around this is the place of the antenna. If you keep the a place of this antenna, this is the main lobe of this antenna. This is called main lobe, and all the remaining lobes are said to be minor lobes. And main lobe is nothing but sorry, main lobe is nothing but the lobe where this particular lobe contains the direction of maximum radiation. Here, that means in this particular area, maximum radiation is concentrated, and in the remaining lobes, minimum radiation is concentrated. And this lobe, which is exactly opposite to the main lobe, is called back lobe. So therefore, so all these are said to be the minor lobes. This is only the main lobe. This is only the important lobe, and all other lobes are wasting the power. The radiation pattern of an antenna is nothing but the uh, plot of radiated power as a function of space coordinates. It is generally radiation pattern is represented by a three-dimensional graph. And here there is a hypothetical antenna that is called isotropic antenna, which radiates equally in all directions. It is not existing, but we assume that particular antenna, if it is able to radiate in all directions, that antenna is said to be an isotropical antenna. Many non-directional antennas, such as dipoles, will emit the equal power in all horizontal directions. With power coupling, with the power dropping off at the higher and lower angles, this is called an omnidirectional antenna pattern. So, a radiation pattern will be containing the main lobes and minor lobes, and generally a lobe is said to be the area around the antenna where the electromagnetic radiation is concentrated. And out of these lobes, the main lobe is said to be the lobe which contains the direction of maximum radiation is called main lobe, and minor lobe are nothing but the lobes except the major lobes are called minor lobes. And uh, one more point is that the principal axis is called the axis through the main lobe is called principal axis, or this is also called Boresight axis. Antenna gain. Generally, antenna gain is an important parameter which will measure the degree of directivity of the antenna radiation. Antenna gain, specifically, this can also be generally synonymously written as power gain of the antenna is nothing but it is defined as the ratio of the intensity, radiation intensity radiated by the antenna in the direction of its maximum output at an arbitrary distance divided by the intensity radiated at the same distance by the hypothetical isotropic antenna. That means simply it can be given as the ratio of the radiation intensity of the antenna in a particular direction to the radiated power of the isotropic antenna in that same direction. The gain of the antenna is an important parameter. High gain antennas are having advantage of longer range and better signal quality and must be aimed carefully in a particular direction. Low gain antennas have short range, but the orientation of the antenna is relatively inconsequential. For example, dish antennas on a spacecraft is a high gain antenna generally, whereas antenna, if it is having equipped with Wi-Fi, it is a low gain antenna that we observe in our laptops. Uh, in practice, half wave dipole is taken as a reference antenna instead of the isotropic radiator. So generally, we know that in order to calculate the gain, generally we take the reference antenna. So for the reference antenna, generally this half wave dipole is preferred practically. The gain is then given by, if we take half wave dipole as a reference antenna, the gain is measured in dBds. So dBd means decibel over dipole. Antenna efficiency. Antenna efficiency is nothing but it is nothing but a ratio of power actually radiated by the antenna to the power absorbed by the antenna by the same antenna. The power supplied to the antenna terminals, which is not radiated, is converted into heat. That means the applied energy, out of the total applied energy, some part is converted into heat. So that is said to be a loss. That heat is generally through the loss resistance. If loss resistance is equal to 0, automatically we get the antenna efficiency as equal to 1. So polarization. Polarization of antenna is The orient is defined based upon the orientation of the electric field vector of the radiated wave with respect to the Earth's surface. So generally, we know the if you take a wire antenna, so if it is mounted vertically, it will give vertical polarization. If it is mounted horizontally, it will give the horizontal polarization. Generally, the reflections generally affect the polarization. Uh, Low frequency, very low frequency, and medium frequency antennas are vertically polarized antennas. So next important topic is beam width. So beam width of antenna is generally defined as angular separation between the two half power points on the power density radiation pattern. And it can also be given as angular separation between two 3 dB down points on the field strength of radiation pattern. It is expressed in degrees. So as shown in this figure, if you see, half power beam width is nothing but the beam width between the two half power points. So this is one half power point on the right side, and this is one more half power point on the left side. So between these 2 points, if we calculate the width in degrees, that is called beam width. And similarly, this is the radiation pattern of a particular antenna. This is said to be main lobe. On either side of the main lobe, there is one null direction, and this is one more null direction. So null direction is nothing but the direction of zero power radiation is called null direction. This is another null direction. So if you take the beam width decrease between these two null directions, that is called beam width between the first two null directions. So therefore, simply in shortcut, it is called BWFN, isotropic antenna. Isotropic antenna or isotropic radiator. So it is not physically realizable. It is hypothetical concept. It is generally used as reference antenna to calculate the gain. Isotropic antenna radiates equally in all directions. Its radiation pattern is represented by a sphere whose center coincides with the location of the isotropic radiator. So most antennas gains are measured with reference to the isotropic radiator and are rated in dBIs. dBi, dB stands for decibels. I stands for with respect to the isotropic radiator. Half-wave dipole antenna. So this half-wave dipole, the picture of the half-wave dipole antenna can be seen in the next slide. The half-wave dipole antenna is just a special case of dipole antenna. Half-wave term means that length of this dipole antenna is equal to half of the wavelength at the frequency of operation. That means its length is equal to lambda by 2. Therefore, it is a half-wave dipole antenna. The dipole antenna is the basis for most antenna designs. So to make it very clear, the antenna, if the antenna is to radiate at 600 megawatts, so what will be the size of the half wavelength dipole? So if you see lambda equal to generally c by f, where c is velocity of light. Okay, if you substitute this frequency, automatically lambda is coming about 0.5 meters. Half wavelength means lambda by 2, that is equal to 0.5 by 2, that is equal to 0.25 meters. So 0.25 meters is the length of the half wave dipole antenna for this particular frequency of 600 megahertz. Half wave dipole antenna, as you may expect, a simple half wavelength wire fed at the center as shown in the below figure. So this figure shows the half wave dipole, and this is the representation of the half wave dipole. At the center, we feed the antenna. That means we apply the current to the antenna at the center. So this is called feeding point of the antenna. So dipoles have radiation pattern as downward, symmetrical about the axis of the dipole. So it is a downward pattern. So this is the dipole. If you see, this is the dipole. So this is the radiation pattern, folded dipole. So dipole in its folded form is called folded dipole. The advantage of folding the dipole is that we can increase the input impedance of the dipole. So thereby we get more bandwidth for this dipole. A folded dipole antenna is a single antenna, but it consists of two elements. So sometimes there might be more than two elements. In simple case, here it is having two elements. So it is a folded dipole. The first element is fed directly, while the second one is coupled inductively at its end. Radiation pattern of the folded dipole is same as that of the dipole antenna. What are the advantages of this dipole antenna? If you see, input impedance of the folded dipole is 4 times higher than that of the straight dipole. So typically the input impedance of this half wave dipole is coming about 288 ohms. We have told that it is increasing the input impedance by 4 times. An ordinary half wave dipole is having its impedance as 73 ohms. So if you multiply 73 by 4, so generally you get the impedance as around 288 ohms. The bandwidth of folded dipole is higher than that of the straight dipole. That means this is the advantage. Hedge antenna. It is not in our syllabus, of course. A loop antenna is one important antenna that is in our syllabus. A loop antenna is a radio antenna consisting of a loop of wire with its ends connected to the balanced transmission. That means the shape of the antenna is in the form of a loop. Therefore, it is called loop antenna. There are two types of loops, small loops and large loops based upon the diameter of the loop. The small loops have poor efficiency and are mainly used for receiving antennas at low frequencies. Except for car radios, almost every AM broadcast receiver will be having this antenna built inside or directly attached to it. Technically, a small loop is also known as a magnetic loop. Generally, it is having its circumference of 1/10 of the wavelength or somewhat less. Self-resonant loop antennas are larger. They are typically used at higher frequencies, especially at VHF and UHF, where the size is manageable. They can be used as a form of folded dipole. They have somewhat similar characteristics with that of the folded dipole. Radiation efficiency is also high and similar to that of a dipole. Radiation pattern of loop antenna is a downward pattern. This is the picture of the loop antenna. It can be circular and square loop. So now radiation is received normal to the plane of the loop antenna and nulls are obtained in this direction. Application, it is used for direction finding applications. Next one is transitional antenna. It is not in our syllabus. Rhombic antenna. Rhombic antenna is it is in the shape of rhombus. Here four wires are connected in the shape of rhombus and it will form the antenna. It is called rhombic antenna. It is the highest development of long wire antenna is rhombic antenna. It is in the shape of rhombus, therefore it is called rhombic antenna. These are the radiations given out by these four wires. These are the four wires that are connected in the form of rhombus. Advantage of this antenna is that easier to construct and its input impedance and radiation patterns are relatively constant over range of frequencies. It is having maximum efficiency and high gain can be obtained. Disadvantages are that large side area and large side lobes. Applications of this antenna are called are generally long distance communication for high frequency transmission and reception, and point to point communication and radio communication and short wave broadcasting also. antenna arrays. So similar arrangement of similar antennas is called antenna arrays. Generally, these antenna arrays are generally used to increase the directivity of the antenna. In order to increase the directivity of a single antenna, what we do is that we take many such type of antennas and we are keeping in a particular fashion, which will form an antenna. Antenna arrays are a group of antennas or antenna elements arranged to provide desired directional characteristics. So generally, any combination of the antenna elements can form an array. However, equal elements of regular geometry are usually used. Aguda antenna. This is generally used for TV reception. It is having uh, mainly three elements. One is folded dipole, and on either side we are using a reflector and director. And reflector and director are nothing but the passive elements, and the middle element is the folded dipole. For this folded dipole, we are applying energy to the folded dipole. With that, the folded dipole will be activated primarily, and based upon the folded dipole uh, activation, the reflector and director are also coming to picture so that they will be functioning. Therefore, those are called parasites here. The picture of this folded dipole can be seen here. The middle element is the folded dipole, and this is called reflector. This is kept back side of the folded dipole, and it is the director. It is kept on the front side of the folded dipole, and the length of the reflector is 5% more than the folded dipole. The length of the director is 5% less with respect to the folded dipole. And this is a picture of the folded dipole antenna. This is a picture of the Aguda antenna. This is generally used for TV reception. Radiation pattern is a modified figure of 8 pattern. It is having improved front to back ratio. We can place any number of directors, but we use only one reflector in this antenna. This is radiation pattern of the folded dipole of the Aguda antenna applications. So these are generally used for radio broadcasting and broadcast television, two-way radios, and communication receivers, and radar, cell phones, and satellite communications. Antenna considerations. Considerations are for any antenna, space out is one consideration, and proximity to the neighbors is one more consideration, and operating frequency, output power, and money. These are the considerations. Any questions, please, you can raise. Thank you.